This just in. There are no little green people on Mars. So far, anyway. But there is a vehicle driving around, and soon there will be air traffic too, of a sort. No, it's not science fiction. It is the remarkable work of NASA's Mars 2020 mission, which just last month landed a rover named Perseverance on the Red Planet. And one of the people right in the middle of it all is a French-Canadian systems engineer from NASA's Jet Propulsion Laboratory. Her name is Farah Alibay, and she joins us now from Los Angeles, California, on this stunning excursion into outer space. Farah, it's a great pleasure to meet you. How you doing?
Hi, I'm doing great. Thanks for having me.
Glad to hear. Let's put some background on the record here for those who are watching and listening right now, and then we'll come back and chat. Here are the key objectives of the Mars 2020 Perseverance Rover. They are to explore a geologically diverse landing site, assess ancient habitability, seek signs of ancient life, particularly in special rocks known to preserve signs of life over time, gather rock and soil samples that could be returned to Earth by a future NASA mission, and demonstrate technology for future robotic and human exploration. That's the mission. Why is Percy so special? Let's start there.
Well, Perseverance is looking for signs of ancient life on Mars. So it's the first mission that is actually an astrobiology mission, meaning biology outside of Earth. And so that is a remarkable goal, right? And so Perseverance has landed in an area called Jezero crater on Mars. Jezero crater is an ancient dried up lake bed. Specifically, what it had is it used to have a river that fed it water and then a river flowing out of it. And we've landed close to the delta of that river. Now, deltas on Earth, when you look at those types of environments, they have lots of sediments, lots of life. That's where a lot of biodiversity exists. So we're hoping that if there had been life on Mars in the past, that could be a good target. Now, as you mentioned, we're not looking for little green men on Earth. The reason why we're looking for, on Mars, the reason why we're looking for life on Mars is because, we think that about 2 billion years ago, Mars looked like Earth. We know it had liquid water, it had an atmosphere, it had a magnetosphere. And so if we look at Earth 2 billion years ago, here there were microorganisms. We're talking cells or little complex molecules, right? So that's what we're looking for on Mars in that particular environment.
There was a previous rover mission, Curiosity, almost a decade ago. What is the difference between Percy's mission and Curiosity's mission?
Yeah, so Curiosity landed in 2012. I was actually a mere intern when it landed. It's one of the reasons why I fell in love with JPL, the place where I work, because I was an intern there and saw the landing happening, saw the team that landed this thing. But Curiosity was focused on geology, was focused on finding evidence of water on Mars and, ancient water, obviously, and so it was a building block towards Perseverance, but didn't have the same scientific goals. And of course, Perseverance is a upgraded version of Curiosity as well. So we used a very similar design, but we have an extra computer. We have a brand new end effector on our arm with brand new instruments. We have upgraded turret instruments and upgraded wheels too, which are hopefully going to allow us to have much better driving performance on Mars.
Now, Farah, I notice I've on a few occasions used the nickname of the rover, Percy, but I notice you never do. So I'm wondering, have I committed a faux pas here by doing that?
No, it's totally fine. I like the word Percy too. But it's just a habit of calling it Perseverance. But no, it's a sweet name for Perseverance to call it Percy. And we do get attached to rovers on Mars, so it's great to hear people kind of also personify it, because we certainly get really, really attached to our little robots.
Understood. Now, it was built in Southern California. Yes. How long did it take?
Well, it's hard to put an exact number. The idea for Perseverance came along in about 2012, right after Curiosity landed. We were like, okay, what are we going to do next? The actual build started somewhere around 2014 with all the components. And so, if you take it from 2014, that's about 6.5 years. But we were building on things that we had learned from Curiosity, right? So we reused a lot of those components, a lot of that concept. So I feel like with every Mars mission, right, we can put a number and say, yeah, it took about 6 years to build, but it's building on decades of experience and decades of development as well.
And how does it actually send the data that it collects back to us here?
By radio. So we have an antenna on a couple of antennas on the rover, and then we have these really, really big antennas on Earth. We're talking 34-meter wide antennas, so not like something you like a dish on your house or anything. And so that's part of the deep space network here on Earth. We have centers in 3 different places on Earth that allow us to talk to all of our spacecraft in the solar system. But one of the things that's really interesting with radio, right, is that it's electromagnetic emission, and so that goes at the speed of light. But Mars is so far that a signal from Earth to Mars right now takes about 15 minutes to get there at the speed of light, and then another 15 minutes to get back. So we don't do real-time operations on Mars, right? We don't just send a command and then sit there for 15 minutes for it to get there, wait for something to happen, and 15 minutes for it to get back. That would be extremely boring days. What we do instead is that we send batch commands. So we'll send a whole plan for a full day. That will take a little while to get to the rover. The rover does its thing during the day and then sends us back information at the end of the night.
I see. How long did it take the rover to get from Earth to Mars?
It took about 7 months. So we launched on July 30th of 2020, and then we landed on February 18th of 2021.
And how fast does it go?
So, when we were traveling in space, we were going at, millions of miles per day. But on Mars itself, it's actually a fairly slow rover. And that's because, on Mars, we don't have roads, we don't have maps. And so when the rover drives on Mars, and it can self-drive, by the way, it has to build its own maps. It has to take its own images, make decisions about obstacles, and then drive on those maps as it's building the next step. So we can only really drive at about 120 meters per hour. So that's like an American football field per hour. It's pretty slow, but for us, those are blistering speeds. That's the fastest any rover has been able to go on the surface of Mars.
I would like to share the footage of the rover landing on Mars, which was really quite spectacular, and then the celebration at Master Control, which was also pretty spectacular. So let's take a look at that, and then we'll come back and chat.
Skycam maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
You weren't too happy at all about that, were you?
Well, it was, years of work, as we talked about, and months of traveling. And you know what? Those last 7 minutes, which are the time when you enter the atmosphere of Mars all the way down to when you touch the ground, we call those the 7 minutes of terror, because that's a fully automated sequence when you have to, you're coming in really, really fast towards Mars, and you have to slow down to a few meters per second to touch down safely. And there is nothing we can do, right? We talked about the fact that the radio signal takes so long to get to Mars. So everything has to be automated. We were just watching the results happening. And I can tell you, I was pacing around mission control. We were supposed to stay at our desks and look all proper, and I could not. I was so stressed out. So definitely, I think for all of us, when we heard that moment, touchdown confirmed, I still get chills watching that video with you, right? It's kind of like it takes me right back, because it was years of work, and for that one moment, right? That's like completely out of control at that point. But it all worked out, and obviously we're having a great time on Mars right now.
I asked the question about how you felt about the whole thing because on the one hand, as you point out, a ton of work goes into this moment, and obviously everybody wants it to be successful. On the other hand, there are no people on that mission, right? There's not an astronaut in a cockpit somewhere. And I wonder if you've ever had a chance during your career to compare notes with other people who've been inside Master Control when there have been people and when they do bite their nails because it's life and death of a different way. Have you ever had those conversations?
Yeah, I have. And of course, it's completely different, right? So when we talk about human systems, they have an extra level of redundancy. They try and reduce the risk a lot more, right? Like, landing on Mars, this was only, maybe the seventh or eighth time that we've landed on Mars. We don't do that all that often, right? Launching astronauts to space, we do that a lot more often. There's a bigger test campaign that goes into that. In fact, part of our mission is to help pave the way for humans. We're learning what it takes to land on Mars. We're learning about the Martian atmosphere, for example, to eventually pave the way. So it's a very different game when we're talking about humans. But of course, when you're talking about humans, it's all about human safety. The stakes are much higher. But still, it's not to diminish the stakes that are, for these types of missions. It's still years of work, thousands of people in the entire world watching. But of course, the severity of things going wrong is much less, and I think this is about as much as my heart can take, honestly, right now.
Okay, well, the last thing I want to do is give you a heart attack in the middle of this interview. So let's change focus here for a second. How do you intend to get the material that the rover will collect on Mars back to Earth, and when?
So right now, Perseverance is going to be driving around the surface of Mars. It's going to be looking for these varied samples. And on board the rover, we have a caching system. So our end effector has a coring drill that will take samples and put them into tubes. Those tubes will get analyzed and then sealed. And then eventually, when we find, when we have enough samples, we call that a cache, we will deposit that cache on the surface of Mars. And then the goal is that we would send another mission to go get those samples. So we would launch a mission to land on Mars, go fetch those samples, put them in a little rocket, and bring those samples back to Earth. So you think like launching a rocket on Earth is hard? We're going to try and do this from Mars. And that is all brand new technology. We've never launched a rocket from another planet. So, we're already working on that mission. The current goal is for that to launch likely around 2026. So right now, our timeline has us bringing those samples back in the early 2030s, probably around 2031. We'll see how that, we have to invent technology. So we're going to see how that goes. And I know that for listeners, right, you're like 10 years from now, that's how long it's going to take you to get these samples back. But for us, right, it's just, like I said, we're paving the way. We're trying to figure this out. And 10 years in aerospace is it's actually not that long, considering how many strides we have to get through to be able to bring these things back.
Well, it's basically the amount of time John F. Kennedy said, we're going to put a man on the moon, and then it happened a decade later. That's how these things work, eh?
Yeah, that's about right.
I want to clarify as well, the rover's going to be there for, what, 2 years entirely?
Forever.
Oh, the rover's staying forever.
Yeah, the rover doesn't come back, right? So once we, and I know that's like a little bit sad when you think about it. You're like, oh, Percy, you're staying on Mars forever. But that's how it works, right? We send the rover there and we landed it, and we don't have a way to bring it back. It's too heavy to launch back. And really, Perseverance was designed for Mars, and so that's where she should live. But the core mission for Perseverance is 2 Earth years, 1 Mars year. And so by that, what we mean is that we want to collect all of those samples, all of those interesting samples in those first 2 years so that we can convince ourselves that we have something interesting to bring back, right? But we certainly expect the mission to last a lot longer than that. The mission is designed with margin to last at full performance for 2 years. But for example, Curiosity landed on 2012. It was a 2-year mission. And now in 2021, it's still operational. So we will continue to talk to Perseverance and continue to operate it for as long as it's alive.
Gotcha.
Basically.
Okay, here's a bit of an odd question, but I want to know exactly what you do. What's your job?
Yeah, so my role, I'm a systems engineer, and I kind of always say that I'm a bit of a jack of all trades. I work on all sorts of different aspects of the mission. So leading up to launch on this mission, I was working on the mobility system for the rover. So I was working on all of the testing that has to do with making sure essentially that the rover doesn't get lost on Mars. There is a copy of Perseverance called Optimism that we use here on Earth in the Mars yard, which is essentially like a big sandbox where we do all our testing. So I was a part of that team. Now on Mars, I'm part of the operations team, and I work not only in day-to-day operations, but I'm also the integration lead for the Ingenuity helicopter. So my job is to coordinate all of the activities between the Perseverance rover and the Ingenuity technology demonstration.
And the Ingenuity helicopter is what?
Okay, so it's a tiny helicopter that's currently tucked in under the rover, and it's what we're going to do is we're going to attempt the first powered flight on the surface of Mars. So think of it as it looks a little bit like a drone. It's a little helicopter with counter spinning blades, and we are going to try to fly for the first time on another planet.
And there it is. It doesn't look like
there she
it's
is.
that. Now you call that a helicopter, even though I guess it doesn't look like any helicopter we're accustomed to seeing.
It's a Martian helicopter, yep. And it's, to give you an idea, it's only, it weighs about 4 pounds, so 1.2 kilograms, and the blades are about 4 feet long, so about 1.2 meter long. So, and that is just about the right ratio, we hope, to be able to fly on Mars. The Martian atmosphere is only 1% of the Earth's atmosphere. Now, gravity is about a third, but air is what we need for lift. So it's certainly a really interesting challenge to even attempt to fly on Mars, let alone the fact that it all has to be automated and that we have to land safely on the surface where we don't have a nicely flattened out helipad. We've found an area that we think is flat and safe, but there's all sorts of challenges involved with flying on Mars.
I think we got some viz of it doing its thing. Sheldon, you want to give that a whirl? Okay, who or what is operating that thing?
So it is all automated. So what we do is that we will plan these flights ahead of time, and we have a team that we have pilots on our team who will design the flight path, and we send instructions to Ingenuity actually via Perseverance. We send them to Perseverance, and Perseverance can communicate with Ingenuity, and we will tell it, okay, on this day you're going to wake up and you're going to fly at this time in this particular pattern, and then during that time Perseverance will be doing observations, taking videos of it, and also communicating with it to understand how those flights are going. So that is a huge challenge. We don't have an onboard pilot. We don't have a way to react in real time to any anomalies. We have to rely on the helicopter fixing itself and landing itself back down if there's an issue.
Well, that was my next question. If something does go wrong, who fixes it and how?
There is kind of no way to fix it. That's the challenge of Mars, right? Is we automate things as best as we can. We build in what we call fault protection of, okay, if certain things happen, we teach, the helicopter how to react. But if anything goes out of our control, well, there's really nothing we can do. But that's kind of part of technology demonstrations. We're trying something new, bold, and, we're pushing the edges of technology. And sometimes that might come with failure, and that's okay, because even if we fail, we've learned something. We've learned something about what it takes to fly on Mars, and that's the whole point of this tech demo.
Now, I gather next month, Ingenuity is going to try to become the first flight ever on another planet. Is that right?
That is correct.
What's the latest on that?
The first powered flight on another planet. We have had balloons. The Soviet Union and the Europeans did have balloons on Venus, but this would be the first powered flight. So right now, Ingenuity is tucked in under the belly of the rover. We're actually at the location. We found an area where we want to fly, and the rover has now reached the location where we're going to drop the helicopter. So over this week here, what we're going to be doing is, the helicopter is currently horizontal. So we're going to slowly deploy the helicopter. There's all sorts of restraints that we have, and we have to get it vertical and then drop it on the surface of Mars. And once we've dropped it on the surface of Mars, we'll back away from it. We'll place the rover at what we call a rover observation location. So it's an area away from it where we can watch all the flights. We're going to do all sorts of checkouts with the helicopter. That's our commissioning process. And then we hope here that in early to mid-April, that we'll be attempting that first flight on Mars.
How do you know? I guess I want to know how if you're testing something on Earth, how do you know that the helicopter is going to react the same way on a different planet with a different atmosphere and different gravity and all that?
That is, it's just as hard to build our testing system as it is to build the system themselves. So the way that we tested the helicopter on Earth is that we actually used what we call a thermal vacuum chamber to pull out atmosphere. We can basically suck the atmosphere out of that chamber and backfill it with just about the atmosphere level that Mars would have. And then the engineers on that team also built a gravity offset system that was able to, to pull out about a third of the gravity. So it kind of like loosely held the helicopter to reduce its weight to one third of its weight, one third of the weight that it would be on Earth. So to give it its Martian weight. And that's how we did all of our testing. So for some of those easier flights, we were able to, our first flight will essentially be a hop. We'll fly to about 3 meters high and hold and then land again. We were able to test something similar on Earth. But for some of the longer flights, we have to rely on physics and kind of hope that what we have in testing and what physics tells us will apply, and we'll see how that goes. But there's certainly challenges with Mars, right? Like the weather can vary, the winds are a little strange. So we're doing the best we can with the information we have, but we'll certainly learn a lot from these experiments.
And just to show that you engineers are not all brain, but you're actually quite a bit of heart as well, I'm going to ask our director to bring up this next picture, because here's a picture of the Wright brothers, who, of course, took the very first flight back in 1903. There's a neat little homage to the Wright brothers that is a part of this whole thing. Do you want to tell us what that is?
Yeah, so we actually have a small piece of the fabric from the Wright brothers flyer, the first flight on Earth. We got a little piece of that, the fabric from that flyer, and it is installed on the helicopter, and it is now on Mars. So we're taking some of that heritage from that first flight and took it with us to honor that achievement on Earth and bring that to hopefully what will be the first flight on Mars.
That is fabulous. Can I ask you this? I've heard you use the expression, I'm on Mars time, or I'm on Martian time. What do you mean by that when you say that?
Yeah, so you remember a little bit earlier when I talked about the fact that there's delay in communication and that we don't operate things in real time. So I mentioned that we operate things we make a plan for the rover and then send that in batches. So what we actually do is that we work during the Martian night. I got a PhD and I'm working the Martian night shift. I'm not quite sure where I went wrong there. But so what we do is every night when Perseverance goes to sleep, she sends us a whole bunch of information, images, data, tells us how her day's been, basically. We analyze all of that. And then as a team, we prepare a plan for the next sol. A sol is a Martian day. And so we do that overnight. And then in the morning, when Perseverance wakes up, we send her that information. So my day starts at about 1800, 6 p.m. every night on Mars. Great. Okay, that's the Martian night shift. That just means working nighttime, right? Well, the problem is that a Mars day, which is a full rotation of that planet, is 24 hours and 40 minutes. So that means that even though I start my day on the same time on Mars every day, my day shifts by 40 minutes every day on Earth. So for example, today I'll be going in at 4 o'clock, 4 p.m. Tomorrow I'll be going in at about 4:40, then 5:20, and so on. So I basically have 40 minutes of jet lag every day, which can be quite difficult for my body.
I want to check out something that I heard about you, and since I've got the source right here, let's find out if it's true. I'm told that you wanted to be an archaeologist, which is, I guess, about the exact opposite in some respects of what you're doing right now. And then you met Tom Hanks, and that changed everything. Is that true?
Yeah, I wish I'd met him in person, but yeah, that is true. So I grew up in the 90s. So I grew up with Jurassic Park and really wanted to be an archaeologist. And then one day when I can't really remember if I was 8 or 9 or something, but I watched Apollo 13. And that movie changed my life. I think, it not only was it about exploration and made me want to become an astronaut, which is still a dream of mine, but also just seeing the teams work together, talk about having to come together to save humans and the stakes that are involved with missions like these. I just remember the scene where they have to fix something and they throw everything they have on the table and literally have to get a square peg in a round hole type of problem. And I just remember the team working together to achieve the impossible. And I thought, this is the kind of thing I want to be part of. And space was just so fascinating. I think what fascinates me the most is that what we do is beyond what a single person can do. And that's the beauty of engineering and STEM as a whole, is that people come together to do things that are greater than themselves. And that tied with that idea of exploration. I fell in love with that when I was young, and that's how I ended up pursuing this path.
It's interesting you had such a positive reaction to that because, of course, I mean, I remember that mission well. I'm a lot older than you. And that's the one where they all almost died. And yet you did not get scared off by that. You embraced that. How come?
Yeah, it's funny because I remember my brother also watching this movie with me, and he was really into space at that time. And that's when he turned away and was like, there's no way I'm ever going to be an astronaut, because he was so scared. But for me, yeah, yes, it's scary, right? Yes, things went wrong. But isn't it incredible that with all those things that went wrong, we still got those astronauts back safely to tell the tale? And that is incredible, because there's more than one thing that went wrong in that mission. And to me, that is amazing. And also, if we think about it, yes, tragic things have happened, and yes, things have gone wrong. But if you look at how much we've achieved in the past 50, 60 years in space exploration, it is incredible. And I think it's a highlight of human achievement that we've made such progress. And now, we're talking about flying in other worlds. We have humans living in orbit of space. That's science fiction, right? Almost.
Farah, I have time left for one more question, and I'm not going to pretend that it's the most important question I'm going to ask you. But since you are from Joliette, Quebec, I do need to know, what's your favorite hockey team in the NHL?
I'm a Habs fan through and through.
Farah, how in heaven's name did you get booked on this show? I have a rule about Habs fans and this program, and I just don't understand it. Well, somehow my security system is clearly not working very well anymore. But anyway, it was an absolute delight to meet you, and we wish you just great good fortune with all of your endeavors. And thank you for sparing so much time for us here on TVO tonight.
Yeah, thank you for having us. And I hope everyone will be following along with Ingenuity's first flight here over the next month.
Amen to that.
The Agenda with Steve Paikin is brought to you by the Chartered Professional Accountants of Ontario. CPA Ontario is a regulator, an educator, a thought leader, and an advocate. We protect the public. We advance our profession. We guide our CPAs. We are CPA Ontario. And by viewers like you. Thank you.